Right, good morning everyone. Okay, so we will continue with our tutorial question from yesterday. Okay, so yesterday we have already solved 2 questions. So today we're going to solve another 3 questions for the tutorial. So let's see if we have time. Maybe I will start on chapter 3 lecture, because as mentioned to you, we will have our lecture lah, our test on week 7, right? So week 7 Monday. So we have a little bit of time so that if I can start first on lecture chapter 3, then we will have time to do a little bit of practice before the real test on week 7. But let's see how it goes. If it takes too long for the tutorial, then it's okay. We have another class on Thursday or Friday, depending on your schedule. So Thursday and Friday, you have each day will have 1 tutorial session. So again, I've done the invitation for the tutorial session according to your section of your tutorial, T1 and T2. But if you want to swap, you just inform me. You can swap the schedule according to your availability lah. Right? Okay. So yesterday we have already solved 2 questions related to designing reactors, of which we were able to calculate the volume of the reactor, single reactor, single PFR or single CSTR, as well as reactors in series, which involve CSTR in series or PFR in series. So yesterday both questions were focusing on using the table. So you remember, the table will provide us with the 2 information, which is X and its responding, or its minus RA related to that X. Meaning, if let's say your minus RA is 0.2 from this table, then subsequently its minus RA is 0.050, so on and so forth. So using the information, we were able to calculate the volume of the reactors, be it single reactors or reactors in series. Okay, so that was what we solved yesterday. So today we have another 3 questions, of which now we are using Levenspear plot. So if you remember, in the class when we were discussing about chapter 2, I have reminded you several times that the information of the minus RA and the X can be given in the form of a table, like what we learned yesterday, or it can also be given in the form of Levenspear plot. But Levenspear plot, you have to be very careful, because Levenspear plot, the plot is actually X, okay, your conversion, versus 1 per minus RA. So that is the big difference, that now the plot is X versus 1 per minus RA. So meaning to say that, for example, in this table, so in this figure, if you see, for example, at my conversion 0.1, my 1 per minus RA, when my X is 0.1, is 2.7. Okay, meaning that when my X is 0.1 or 10%, my corresponding 1 per minus RA is 2.7. Okay, so if you remember, if it's in the form of table, it is X and minus RA. So the difference is very obvious, because later on when the calculation, if you remember, we will always have to find the value of the minus RA, right? But in this plot, is no longer given in the form of minus RA, is given in the form of 1 per minus RA. So it's very important for you to differentiate how do we substitute the value in the equation. Okay, so let us try the question and see whether it is okay for you. So as I mentioned previously, questions are not difficult if you realize, but it's always processing the information, identifying the numbers, and knowing that what the number represents is always the challenge. So let's say you're not sure the number represents what, that will cause the problem, right? But before I forget, the lecture on last Monday and the lecture yesterday, I've already uploaded on your VLE. Okay, you can watch it on VLE directly without the need to download, because the link is from the YouTube link. So meaning that I use the YouTube link, I embed into your VLE. So you can watch it directly from your VLE, or you can also go to the YouTube directly. The tutorial as well. So the tutorial yesterday, I have already uploaded under the tutorial part. The tutorial questions are also on VLE already. So the questions and the tutorial discussion yesterday is also on VLE. The lecture yesterday is also on VLE, right? So that's for your reference. Okay. So this question below, this is the gas phase reaction. Okay, so by now you already realize that knowing the phase of the reaction is very important. Perhaps in some situation it's not so relevant to the question, but in certain situation it's very relevant. Okay, regardless of that, you just take into consideration, okay, this is going to be a gas phase reaction, right? And then the reaction is A producing B plus C. Okay, and using the Lorentz plot for the reaction, so this is your Lorentz plot as given here, right? Determine the inlet molar flow rate of reactant A. Okay, so the questions started with telling you what do they want. Okay, so again, if you remember, there are certain variables that is very important for you to really remember, understand, and know what it is. Okay, so the first key here is that they say molar flow rate. Okay, so you have learned that if it's molar flow rate, mole per time, we will always use F to represent molar flow rate, regardless of which compound, regardless of inlet, outlet. Whenever we talk about molar flow rate, we represent it with F. Okay, concentration is C, volumetric flow rate is epsilon. Okay, so these three you really cannot forget, or you really cannot get it confused. These three are always very important. Okay, so in this case, it's molar flow rate is F. And then you know that molar flow rate always must refer to certain chemical or certain compound. Okay, so in this example, you have three compounds. So it can be molar flow rate of A, it can be B, or it can be C. But they mention of reactant A. Okay, so meaning to say this is the molar flow rate of compound A. Okay, so it can be either Fa or Fa naught. So what's the difference? Fa naught is always referring to the inlet molar flow rate. Naught is indicate zero or indicates the initial molar flow rate of A, Fa naught. Or Fa is the outlet molar flow rate of A, or I can say the molar flow rate of A during or after the reaction. Okay, so when you check back the question, they clearly mention inlet. So they say that this is the initial molar flow rate of A before the reaction takes place. Okay, so this is Fa naught. So you already identify from the question. If it's me, I will just write straight away that I know the questions wants me to find Fa naught. Okay, so regardless of what first, at least now I know that they want you to find Fa naught. Okay, so at least you know what you are trying to find from the, what do the question wants you to find. Okay, so I put it as question mark lah, because this is what we want to find. Okay, so they say for a 30 dm cube single PFR and a 30 dm cube single CSTR. Okay, so they say that they want you to find the molar flow rate, and you have two different reactors. Okay, the first reactor is a PFR, one PFR, and you know that they give you 30 dm cube. So I'm sure that you know dm cube is definitely volume, right? It's a dimension of volume. So instead, in fact, they are giving you the volume of that one PFR, which is 30 dm cube, as well as this another reactor, which is a CSTR, also a single CSTR, and the volume is also 30 dm cube. So you can imagine now that you have two reactors. It's a single CSTR. You have another single PFR. Okay, both of equal volume. Okay, all right. And then they say to achieve the final conversion of 20%. So they say that the conversion that is to be achieved in both the reactors are 20%. So your X is 0.2. Okay, so again, I repeat, okay, if you forget the concept of conversion, conversion is referring to the conversion of your reactant, how much percentage or how much fraction your reactant A has been converted. Okay, so in this case, we have only reactant A. So meaning that in this reactor, only 20% of A is converted into B and C. Okay, so this is the clue, right? So in this question, you realize that if I always remember, I always told you the first thing is to always write down what you know from the question. Okay, make sure that you synthesize the information clearly. In any engineering question, it's always the same. synthesizing information. In fact, when later on, when you go to the real world, it's also the same. When you're dealing with engineers, technicians, technologists, you're dealing with managers, it's very important to understand the information given to you, right? So in this case, the three information that we know so far is that the volume of PFR is also equal to the volume of CSTR, which is 30 dm cube, and that we have the conversion X of 0.2, and the question wants us to find FE naught. Okay, so meaning that when you have two different reactors, you have to find two FE naught, the FE naught for CSTR, the FE naught for a PFR. So they want us to actually determine if I have one PFR, one CSTR, I want to achieve the same conversion for the same reaction, what will be the molar inlet molar flow rate or the initial molar flow rate of A, which is FE naught. Okay, so in this type of questions, of course, at this early stage of reaction, you know there's not many yet of equation that you know. So maybe at this stage, it wouldn't be that difficult for you to find the correct equation. But later on, when you learn further and further into reaction, it will become a very big challenge because you have too many equation, right? Okay, so at this stage, the easiest way for you to formulate, or the easiest way for you to strategize the correct formula is, again, for me personally, is to come out or to deduce from the information given. So the only information given is actually very limited. You're only given the volume and also the conversion. So you know that up to chapter 2, you have learned the design equation for single CSTR, the design equation for the single PFR. So you know that the design equation for these two reactors is to find the volume, or the two equations will have the volume. So you can already correlate that definitely these two equations will be involved because you are given the volume. And also you remember both design equation, PFR or CSTR, the single reactors, they also have conversion. So you remember that both equation both equation has the parameter of volume, both equation has the parameter of conversion. So you know that somewhat you are on the right track because these two equation has the variable that you know. As well as, if you remember, both equation also have FA naught. Okay, so you can correlate that I have three variables. Okay, two variables I know the volume, I know the X, I do not know FA naught, but I remember that all these three variables is in one equation. So it's very likely the equation that you choose is correct because you have the unknown and the known variables in one equation. Okay, so let us start first with, let's say, CSTR. We start with PFR. Okay, since the step here start with PFR, we start first with PFR. Okay, so you have to again come back and remember that PFR, the design equations involve integration. Okay, so the formula will be volume of PFR equals to FA naught. So you can see now, even at this stage, even if I don't go to the back, you can see volume PFR you already know, right? 30 dm cube. So there's one known variables that you already know. Next one equals to FA naught. Okay, so that is the unknown that you don't know, right? That's the variable that you do not know. Okay, so you already have one you know, one you don't know. So you can realize that probably you're already on the right track because you already have one known variables, one unknown variables. But you have to go to the end of the equation. So the end is an integral. So the integral, again, if you remember, the integral, you must be very careful when it comes to PFR because it's very important for you to know the PFR is converting from what conversion to what conversion. That forms your bottom limit and your upper limit. So in this PFR, they're converting from 0 to 0.2, meaning from a no conversion of A until achieve 20% conversion of A. So it become 0 to 0.2 dx per minus RE. Okay, so this is the integral formula. Okay, so let's say at this stage, you just want to make sure, are you on the right track? Okay, although it's an integral equation, I understand, but you can see the variables are X and minus RE, right? So again, you know that X and minus RE is something that I can obtain from Leven's sphere plot, meaning the point here is that X and minus RA are the known variables because I can get it from the level-square plot. So if you remember CPP, you have learned degree of freedom analysis. So what is the purpose of degree of freedom analysis? Is actually to help us to determine first whether the equation can be solved or not with the information that you know and the information that you don't know. Okay, so at this stage, you know that you have one equation. So you know that the degree of freedom analysis tells us that in order for us to solve the equation or to solve the variable, one equation you must have only one unknown, meaning that the number of unknown cannot be more than the number of equations. So if I have two unknown, I must have at least two equations. Three unknown, three equations. The unknown number cannot be more than equation. So you have, let's say you have one equation, you got two variables, sampai bila-bila pun you can never solve because the unknown are more than the number of equation. So this is what I'm trying to teach you. So you can see from this equation, I know volume, I know X, I know minus RA from the level-square plot. Volume is from the information. And the only unknown that I do not know and which I want to find is FA naught. So at this stage, even before I proceed to the next one, I already know that I can solve this equation and I can get FA naught. Okay, so that's the key here whenever you do engineering question. If you have one equation, you can only solve if only you have one unknown. If you have more than one unknown that you do not know, it means that you have to find another equation. Selagi kamu tak cari the next equation, the second equation, you can never solve if you have two unknown. Okay, so that's something that you can learn during when to solve engineering problem. Okay, now that you determine that you have enough information and enough equation, then we proceed. So you remember that when we have integral equations in design of PFR, we will convert it into Simpson one-third rule. Okay, we learned, right? We learned that the integral part of the PFR is actually equal to the area below the curve. So area below the curve can be represented by Simpson one-third rule. Okay, so again, Simpson one-third rule, I keep repeating, it's not difficult, but you know that at the back part, you have three different minus RA that you have to substitute. And the minus RA that has to be substituted depends on your conversion. And the conversion is something that you have to check from the question. So from this question, again, the initial X is 0. That's why the first point will be 1 per minus RA when my X is 0. Okay, again, it means 1 per minus RA when my X is 0. Okay, so you can check, you can even from this point, you can already go to the level-square plot, you can check. Okay, when my X is 0, my 1 per minus RA is 2.2. Okay, you can see from this level-square plot, when my X is 0, my 1 per minus RA is 2.2. So you can see here, if I go to the next point, you can see that I can replace straight away with 2.2 over here because 1 per minus RA when my X is 0 is 2.2. So it's important, okay, let's say if you forget, when using level-square plot, the value given to you is directly 1 per minus RA. That's why we can directly substitute the value. However, when yesterday when we are using the table, you realize that the table gives us X versus minus RA. That's why you will have to divide the value because the value was minus RA. But when we're using plot, they give us directly 1 per minus RA. That's why you can directly substitute the value from the level-square plot. Okay. Then we go to the back part. Okay, the back part, you have to really remember the back part is actually 1 per minus RA at your upper X or your final X. So in this reactor, the final conversion was 0.2. So the last point will be 1 per minus RA when my X is 0.2. So if you realize when I explain to you the tutorial question, I will always go first point and the last point because when you get the first point correct and the last point correct, then the middle point should not have a problem. But if you do not know the right initial point, the right final X, that is where you may have problems in determining the middle point. Okay, so the last point will be 1 per minus RA when my x is 0.2. So again, you can go to the plot. So when my x is 0.2, my 1 per minus RA is 3.33. Okay, so I can directly substitute into the back point as 3.33. Okay, so here is 3.33. Okay, so okay, done, right? Okay, then I will only go to my middle point because again, I cannot determine my middle point or my middle x until I know the initial and the final. So the middle x, the formula will be 4 over. So again, the 4 is the Simpson one-third rule formula. Okay, the formula will be 1, 4, 1. So the 4 always remain regardless of the condition. Is 4 per minus RA at my middle x. Okay, so you have your initial x was 0, your final x was 0.2, hence your middle conversion will be 0.1. Okay, so meaning you will have to find 4 per minus RA when my x is 0.1. Okay, again, I have to keep emphasizing is 4 per minus RA when my x is 0.1. You don't multiply with the 0.1 because when I put it 0.1 here, I have a worry that you will assume you have to multiply 0.1. You do not multiply 0.1. It's just we put it there so that you know your minus RA is at which conversion. Okay, so again, you go to the Leonspiehl plot, you can see that when my x is 0.1, my 1 per minus RA is 2.7. Okay, so you can see that I directly substitute with 2.7, but you don't forget we have the 4, right? The formula has a 4. So that's why it becomes 4 multiplied with 2.7. So I hope this part you don't forget. Sometimes students tend to forget the 4 over there because the equation has the 4, but students sometimes may forget the 4 in the equation. Okay, so the front part is already done. So next is the delta x per 3. So again, I mentioned it many times, delta x is the difference of the x between initial to the middle x or middle x to the final x. Okay, so if the initial x is 0, your middle x is 0.1, therefore your delta x is also 0.1, right? The difference, right? Or if you want to find delta x from the middle x to the final x, it's still the same. Your middle x is 0.1, your final x is 0.2, the difference is still 0.1. So that's why we get delta x as 0.1 over 3. Okay, so you can see here that when after I substitute everything, because again, don't forget, we know the volume of the reactor as 300 dm cube. That is given, 30 dm cube. Okay, so we know that the volume of the reactor is 30 dm cube. The rest part at the back part we already saw. So we are only left with one unknown, which is FA0. So again, when you have one equation, you have only one unknown, the rest you have already substitute in the value, then definitely the problem can be solved and you will get FA0 as 55.05 mole per second. Okay, so at this stage, the questions are still, actually it's not that difficult, but it's no longer straightforward lah, because previously you just find volume, right? But now you're finding another variable. So you just, in this question, what is the scenario? So the scenario, imagine now, you have a reactor. The reactor is already available in your plant. Okay, so you have an available reactor in the plant, of which its volume is 30 dm cube, and you have determined that the conversion that you would like to achieve is 0.2, 20%. So you would like to know how much your inert molar flow rate shall be, because you have to prepare your inert molar flow rate. Okay, so you determine from this equation, that your inert molar flow rate that you have to prepare must be 55.05. Okay, so this is a scenario. So the previous example, the scenario maybe you have the targeted conversion, you have the targeted, you already know the inlet molar flow rate, you would like to determine how big my reactor shall be. Okay, so certain questions is to fit to certain scenario of application that you may encounter. Okay, so next one, we should go to CSTR. So CSTR is very straightforward, right? Because we know that CSTR, it doesn't have any integral, so they are quite straightforward. So the volume of CSTR from the formula. So again, I repeat, the formulas are already given to you, just that the Simpson wanted rule, the formulas are not fixed. Okay, for PFR, for CSTR is fixed lah. So but remember also, volume CSTR, the formula may change if you have single or you have reactor in series, right? If you remember. Okay, so when you have single CSTR, the volume of CSTR is given as FA naught X per minus RA. So this is something that you have already learned, right? So again, let's say you're not sure, am I on the right track, okay, whether this equation can be used or not, because I can imagine as you go further, not only you're learning reaction, right, you learn a lot of courses, you have a lot of equation, even if provided also sometimes you have difficulty in understanding or difficulty in knowing, am I using the correct equation? So I always tell you the key is you know first what information given to you. You also must know what that you want to find. Then you can realize whether the equation is enough or not enough to answer. So let's say lah, you have 3 unknowns, okay? But then you only confident of only one equation. So it means it can never be solved, because when you have 3 unknown, it tells you that in order for you to solve that, you have to find another 2 equation, and that 2 equation must have the unknown and also the known variables that you have. So that is the challenge. You must realize it's never enough. If it's not enough, what are the possible next equation that I can use? So in this question, let us check. So we have the variable of volume CSTR, which we already given 30 dm cube. Okay, on the right hand side, I have FA naught, which I want to find. Okay, X is the conversion, which I already know, 0.2, and minus RA at my conversion. So minus RA at my conversion, I can find from Levenspiel plot, which means it's a known variable. So in this question, I only have one unknown, which is FA naught. So this is definitely solvable. Okay, so let us do one by one. So the volume of CSTR is given as 30 dm cube. FA naught is provided to me, sorry, FA naught is given, FA naught is what I want to find. Okay, X is 0.2, okay, the conversion that I want to achieve, and it's minus RE when my X is 0.2. So when I check for Levenspiel plot, when my X is 0.2, instead of minus RE, the plot gave me 1 per minus RA at 0.2, which is 3.33. Okay, so that's why we directly multiply with 3.33, because the Levenspiel plot already gave us directly when my X is 0.2, my 1 per minus RA is 3.33. So it's a direct substitution. And you can solve this and you get your FA naught as 45.05. So you can see that if I have a CSTR, a single CSTR of a 30 dm cube, okay, I need my FA naught, my inlet molar flow rate of A, to be at least 45.05 to achieve the conversion of 20%. Okay, so this is how you solve question number 3. So as usual, I will give you 1 to 2 minutes. Okay, if you are doing it or if you need time to catch up, okay, I will come back in 2 minutes, 1 to 2 minutes time to continue the next question, right? All right, so we will continue to the next question. I hope you are still okay. All right, so you go to the next question. Okay, all right. So next question. Okay, so you can realize that the questions are becoming harder and harder lah. Okay, I try to increase the difficulty level by level so that you won't feel shocked as the question comes in. All right. So the next question is question number 4. So we have 2 more questions. All right. The gas phase reaction is given as follows. Okay, so the irreversible reaction is carried out isothermally in a flow reactor. Okay, so at this stage, the first sentence does not really significant to you because we have not yet go into designing reactors considering irreversible, reversible reaction, isothermal, so on and so forth. So the first sentence at this stage is not so significant to you. It doesn't really affect your calculation. But later on, when you go to chapter 3, okay, when we start chapter 3, you will realize, oh, this information is also important to us, right? Okay, so the feed mixture, okay, the feed mixture means your inlet mixture consists of 40 mole percent inert and the balance reactant A. Okay, so you already given quite a little bit weird information, right? Previous questions, we have not yet encountered this, but now they give us the information of your initial mixture. Okay, so they say that initial mixture that I have before the reaction takes place contains 40 mole percent inert and the balance is reactant A. So if you check back, your reactant is only one reactant A. But in this question, they do not use 100 mole percent of A. Instead, the mole percent of A is actually only 0.6 because you have inert of 0.4, the mole fraction, right? So remember, when you're given mole percent, you must convert to mole fraction. So in this question, actually, we can determine the initial mole fraction of an inert and an initial mole fraction of A. So you always must understand, in reaction, the initial compound is not necessarily only the reactant. It may also consist of other compounds that may not be involved in the reaction, but they exist in the mixture together. So for example, as I mentioned, let's say you want to do combustion, pembakaran, right? So combustion is combustion definitely involve oxygen gas, okay? But you know that it's very rarely we use pure oxygen for combustion. Okay, so but combustion is a very low economy, low cheap process, right? So using oxygen gas is definitely not economical. So instead of using oxygen gas, I will use air because our air contains 21% of 21 mole percent of oxygen gas. But you don't forget, our air only contains 21 mole percent of oxygen gas. You still have nitrogen gas, you have a little bit amount of carbon dioxide. So they will not be involved in the combustion. They will not be involved in the combustion reaction, but they exist initially in the reaction. So you can imagine this is somewhat the scenario where initially my mixture does not only contain the reactant A, it also contains the inert. And it's given clearly that our inert is 0.4. So for inert, normally we'll use I, capital I, to represent inert. So mole fraction, we will use Y to represent mole fraction. So this is something maybe a little bit new. We hardly deal with mole fraction, although we have learned previously. Okay, so we will use Y for mole fraction, I for inert, and since this is inlet mixture, that's why it becomes YI0, initial mole fraction of inert as 0.4, and therefore the initial mole fraction of A, it must be 0.6, right? Because the total mole fraction is 1, or we can also say the total mole percent is 100. So if I have 40% inert, I will definitely have 60% of A. So that's the two information I already synthesized from the first sentence. And then they say the feed mixture temperature is 320 Kelvin. So you know that your temperature T0 is 320 Kelvin. So at this stage, okay, temperature we are still considering isothermal reaction, or isothermal reaction, if you know, iso means same, thermal is heat, right? So isothermal means same heat, or you can say same temperature, meaning that during the reaction, there are no changes of the temperature. Okay, so we call it isothermal. But you must also understand that not all reactions are isothermal. There are reactions that can emit heat, produce heat. There are reactions that need heat to be absorbed. Okay, so that case, definitely the initial temperature and the reaction temperature is no longer the same. Okay, so that's why at this stage, it's also important for you to determine T naught is not necessarily the same as T until they mention isothermal. If they mention isothermal, then yes, T naught equals to T. Okay, so T naught is given as 320 Kelvin. Okay, next information. The initial partial pressure of the inert is 5 atm. Okay, so you have already learned, okay, I already taught you in the first 2 weeks, we learned also about partial pressure, right? So you know, in this case, when initially I have A and inert, both are gases, right? Because the question says the gas phase reaction. So in the initial part, I have gas A and gas inert. And they tell me that the gas inert pressure is 5 atm. So this is interesting. They give us the pressure of the gas inert, which is 5 atm. We do not know the pressure of E. We just know the pressure of the inert is 5 atm. So we can use, if pressure, we will always use P. And since this is a partial pressure of inert, so it will be P subscript I. And since it's initial mixture, it becomes PI naught. So initial partial pressure of inert is 5 atm. So this is all the information they give to us. Okay, all right. So this is all the information given to us, right? So they say the Levenspear plot for the reaction is given as follows. So again, they give us the Levenspear plot again. Okay, so you have Levenspear plot, you have conversion versus your 1 per minus RE. Okay, so let us go first to the question. The question says, the reaction was conducted in 2 CSTR in series at initial rate of 10 dm cube per second. Okay, so the first information, I have now 2 CSTR in series. Okay, meaning that I have volume of my CSTR1 and the volume of the second CSTR. Next, they say initial rate of 10 dm cube per second. Okay, so you know that 10 dm cube per second, at this stage, you already learned that dm cube is volume, second is time. Volume per time is volumetric, volume per time is volumetric flow rate. So volumetric flow rate, and they say this is initial. So this is initial volumetric flow rate. So initial volumetric flow rate is given, represented by epsilon naught. Okay, so this is the challenge. If you do not identify it correctly, let's say you assume it's FA naught, you assume it's CA naught, then your entire questions are already wrong at the very first step. So I keep emphasizing, really make sure you know what are the values given to you. So in this case, they give you epsilon naught, right? Okay, done. They say, determine the volume of the both reactor. So it sounds quite simple. They want you to find volume CSTR1, volume CSTR2 to achieve 60% conversion at first reactor. So this is definitely X1, 80% overall conversion at the second reactor, definitely X2. So they give us X1 0.6, X2 0.8. Okay, right. So you already have these two information. Okay, you have epsilon naught, volumetric flow rate. You have X1, you have X2. They want you to find volume. So again, come back to what I taught you just now. Okay, determining the correct formula. So since I want to find volume, okay, I know that I have conversion, I have epsilon naught. So you know that at this stage, the formula are not that many that you learn. You know that if to find volume of CSTR, single or in series, the formula for CSTR in series are these two formula. Okay, so the first formula to find the first CSTR1, FA0 x1 per minus RA at my x1, and the second formula to find volume CSTR2 is FA0 x2 minus x1 per minus RA at my x2. So these are the two formulas that you know that you will definitely use these two formula, okay, to find the volume CSTR1, volume CSTR2. Okay, but let us check. Do we have enough information? So first of all, volume CSTR1 is what I want to find. So that is my unknown. Okay, so I already established I have one unknown that I want to find. Okay, so by right, if already I have one equation, one unknown I want to find, meaning that the rest of the unknown, the rest of the variable must be known, or the rest of the variable I must find the value first, or else I can never get the volume. So on the right hand side, the first variable is FA0. So if you realize in the question, we were not given FA0. The only information given to us was this information. You just check the one that I highlight because I scared you get confused. So we were given mole fraction of inert, mole fraction of A, initial temperature, partial pressure of inert, you're given inlet volumetric flow rate, you're given x1, x2. So you realize that FA0 is not provided to you. Okay, so I have now, the problem is I have now two unknown because the volume is something that I do not know, which I want to find. And now I find that FA0 also I do not know. Okay, so let us look again the rest of the variables. So next one is x1. So x1 I know, x1 is 0.6 because you mentioned in the question, the conversion in the first reactor is 0.6. So x1 I can solve. So next one is minus RA at x1. So again, this information I can check from Levenspiel plot because for my Levenspiel plot, when my x is 0.6, my x1, 1 per minus RA is 8.85. Okay, so meaning to say that I know x1 and I can find minus RA per x1. So now the challenge is that you know that in this question, I have one difficulty because I have to first know FA0. Because without knowing FA0, I cannot solve the volume of CSTR1. So you know that I already taught you, if you have two unknown in one equation, you have to find the second equation. You got no choice. You can never solve if you have more than one unknown in that one equation. So if I have two unknown, I need at least two equation. Okay, so you know the challenge here is that how do I find FA0? Okay, so then again, how do you strategize? Come back again and look at what information given to you. The next information given to you was epsilon naught. Okay, you are given epsilon naught. So if you remember, okay, you know the correlation. There is a correlation between FA0 and epsilon naught, right? Because the correlation is that you know that CA0 is equals to FA0 per epsilon naught. Okay, so you have to remember, this is a bit of, I hope you don't get confused. The original one was you want to find FA0, okay, because you know I cannot solve without knowing FA0, okay. But I was not given FA0, I was given epsilon naught. So the next strategy to remember the next equation that correlates FA0 and epsilon naught. So you remember the correlation was CA0 equals to FA0 per epsilon naught, or I can also write it as FA0 equals to CA0 multiply with epsilon naught. Kan sebab CA0 is FA0 per epsilon naught. Therefore, FA0 equals to CA0 multiply with epsilon naught. Okay, so now again, you check back this equation. This equation, I want to find FA0. Okay, I know epsilon naught. But then again, you are stuck because you have another unknown you do not know, which is CA0. So you see here, the question become a little bit harder because you were not told to find it, but you have to strategize from the information given to you. So the challenge here now, if I can synthesize back, original equation doesn't give me FA naught. I have to find FA naught first. Okay, I know that FA naught can be correlated to epsilon naught. Epsilon naught is given to me. So the correlation is FA naught equals to CA naught multiplied with epsilon naught. So now another challenge is now I do not know CA naught pula. Okay, so that's the next challenge. I do not know CA naught. So means what? You have to find the third equation now because you have the second unknown that you do not know. So you have to find the next equation to correlate pula. Okay, so you have to remember back. What are the other information given to me? So that is the challenge is that you have to go step by step. So now I know that the next challenge is I need to know first CA naught. So again, look back the rest of information that you haven't used. So you realize that the initial information given to you, you haven't used it yet. You know that you have YI naught, YA naught. You have T naught, you have PI naught. So you realize information given to you must be used in some ways or else they won't provide you with the information. So now you have to think back again. Apa pula equation or what are the equation correlates all this? So you remember if you have gas phase and you have temperature, you have mole fraction, you can actually find CA naught from the ideal gas law. So now next step, you can probably synthesize or you can probably guess. Oh, meaning that I have to first find CA naught using the ideal gas law because this is gas phase reaction. So you again, now you have to think back. Okay, the ideal gas law equation tu cukup tak untuk saya solve? Is it enough for me to solve? So you look back. CA naught is what I want to find, right? Okay, so now become the focus of my equation. I want to find CA naught. So the equation give you CA naught equals to the other dual version, right? If you remember, there is two versions of the equation. So let me write back because I scared you worry. I worry that you may not remember there's two different versions depending on information. So the first information, if you have partial pressure of A initially, PA naught, you can divide by RT naught, you can get CA naught. Meaning if you know directly the pressure of A initially, partial pressure A initially, you can directly use that value, you divide by RT naught, you can get CA naught. However, if let's say you do not know the partial pressure of A, so I hope you don't get confused. Why do we need to know partial pressure of A? Because you want to find concentration of A. So when you want to find concentration of A, we must know the pressure of A initially. Okay, that's only by then I can find how much is my concentration. Okay, so the second version, if you do not know the partial pressure of A, but you know the total pressure of the system, meaning initially you got A and inert, right? Let's say you know the total pressure, you can also use, but that is represented by P naught. P naught represents the total pressure that comes from your A and comes from your inert. But when you have the total pressure, you must multiply with YA naught, the initial mole fraction of A, because you have learned in Raoult's law, right? You have learned Raoult's law that if I want to find pressure of A is equals to mole fraction of A multiplied with the total pressure. Okay, so then both also you divide by RT naught. So then you come back and check formula mana that I can use. So the first formula, I do not know PA naught. If you realize from the question, they give you only PI naught, the pressure of inert. I do not know the pressure of E. So very likely, unlikely, I cannot use this equation. Let me check the next one. So the next equation, I have YE naught. I know that my initial mole fraction of A is 0.6. Okay. R, I know, gas constant, I know. T naught, I also know. The initial temperature is 320 Kelvin. But again, another issue, I do not know P naught. So again, if you realize you have the equation, you are from 1 to 1 to 1 to 1. Because again, when you have one equation, I'm stuck because of one variable. I find the next equation. The next equation, I'm stuck with one variable. I go to the next equation. I'm stuck with one variable. I go to the next equation. So you can see it becomes challenging to you because you have to then really understand the steps, or you have to understand how the equations are correlated. Okay, so this is what we call as really problem solving, really knowing that all equations are given to you, but how do we synthesize the steps? Okay, so in this case, right now the challenge is finding P naught. Okay, so again, I can also tell you that maybe some of you will think, why not we find PA naught directly? You also can. Or you want to find P naught, you also can. They are different steps. Okay, but in this today's discussion, I will discuss how can we find P naught, right? So again, when we talk about Rao's law, I told you just now the Rao's law says that pressure of A, initial partial pressure of A, is equal to initial mole fraction of A multiplied with the total pressure. So YA naught equals, sorry, PA naught equals to YA naught multiplied with P naught. The same Rao's law can be applicable to inert gas as well. So meaning that if the partial initial pressure of inert will not equals to initial mole fraction of inert multiplied with the initial total pressure. So Rao's law ni is not only applicable to gas A, it's also applicable to the inert gas. So why I want to correlate with the inert gas? Because I have inert gas information. Because I know that the inert gas partial pressure was 5 atm. And I know that the mole fraction of inert was 0.4. So meaning that I can solve my total pressure. I can find P naught. So from the Rao's law of the inert, I can actually find P naught. So I get P naught as 12.5 atm. So I can already solve. Okay, so again, this is to discuss if I want to find P naught. You can also find PA naught. If you remember, we have somewhat discussed a similar question. In fact, you submitted to me your quiz question. So this is somewhat similar. So you remember I taught you in the class, if let's say I want to find PA naught, I also can do so. Okay, but in this example, I find first P naught. So now what the steps are, once you determine the unknown variable, you come back to the equation. So now I can solve the equation. So PA naught was 0.6, the mole fraction of A. The total pressure is now 12.5 atm. R is 0.082 atm dm cube per mole Kelvin. So again, the R value, you must be very careful. There are many R values provided to you. So how do you know which formula, which R value to be used? For me personally, I follow my pressure unit. So in my example here, the pressure unit was atm. I will find the R value with atm unit. So the only one R value with atm unit is actually 0.082 atm dm cube per mole Kelvin. And the temperature is already in Kelvin, 320 Kelvin. So as solve, I will get my CA naught as 0.29. So now kalau you realize, you are doing back reverse calculation. Sebab jadi masalahnya was, first equation don't have the variable. Go to the second one. Go to the third one. Go to the fourth one. Finally, the fourth equation give you the variable. So now you come back. 4 replace to 3, replace to 2, replace to 1. So I hope you understand. This is the challenge. You have to know 4 will go to 3. 1 goes to 2, goes to 3, goes to 4. Dah dapat 4. 4 substitute into 3, substitute into 2, substitute into 1. Alright, okay, then now I got my CA naught, then I can get my FA naught. So now I go substitute into the second equation because I didn't know CA naught, right? So I know CA naught, I can already get my FA naught. So if you lost the plot, why we need FA naught? Because the initial equation doesn't give us FA naught. So you got FA naught, since you know your CA naught, you know your epsilon naught, then only you substitute into the main equation back. Now only I can find my volume of the of the first CSDR. So the first CSDR, the formula is given as volume CSDR1, I want to find, equals to FA naught. So FA naught I have already solved, 2.9. Multiply with x1 is 0.6. Multiply with 1 per minus RA at my x1. Okay, so you go and check from your table. At 0.6, 1 per minus RA is 8.85. So I will substitute directly 8.85 because that is 1 per minus RA when my x is 0.6 from the table, from the plot. So I get the volume as 15.4 dm cube. So that is for the first CSDR. So actually the final solution is not that difficult, right? But the challenge was that you were not given one unknown, and that one unknown caused you a lot of problem because you have to find the stage of the equation. Okay, so next we go to second CSTR. So now you should not have any more problem because your main problem just now was FA naught. Once you get the FA naught, you can subsequently use in the next equation, no longer a problem because you already find the FA naught for the first reactor. It's the same FA naught for the second reactor. So the formula is volume CSTR equals to FA naught x2 minus x1 per minus RA at x2. Okay, so you will find from the formula, FA naught is still the same, 2.9 mole per second. My x2 minus x1 is 0.8 minus 0.6. So this part you don't forget. Sometimes students forget second reactor formula. So sometimes they directly put FA naught x2. It's wrong. It's FA naught in bracket x2 minus x1 over minus RA at x2. So my x2 was 0.8. So if you check for 11 speed plot, when my x 0.8, my 1 per minus RA was 20. So you have to multiply directly with 20. You will get the volume of the second CSTR as 11.6. Okay, so done for question A. So question A is very long. You can see that I discussed it very long because the final equation is very easy to solve. But the challenge was that you have to know that you have to first find FA naught, and you realize that the FA naught information is not given directly to you. You have to find one variable, the next variable, then only you can solve the equation. Okay, so this is something that you should expect for test or final exam, of which you are not told to find the variables, but you have to formulate yourself. How do you determine that? Following the information given to you. Okay, so we go to the next one, to the next question. Okay, so the next question is that, okay, the reaction was conducted in 2 PFR in series. Okay, so now I have 2 PFR in series, right? So they say, determine the space-time. Okay, so you just learned yesterday about the concept of space-time. Let me refresh back. Sorry, this is chapter 3. Let me refresh back space-time. If you cannot remember, when we just learned yesterday, this was what we learned, the concept of space-time. Okay, we learned the concept of space-time. Sorry, I hope you can see this. We learned the concept of space-time. Space-time is the time needed or the time, the holding time, how long you will hold your reactant in the reactor before it has to be flown out. So space-time is represented by tau, and tau is given as volume of the reactor divided by the initial volumetric flow rate. So again, I repeat, space-time is given as the volume over initial volumetric flow rate. Okay, so now that we have refreshed back, we can then realize how do we correlate. Okay, so come back to the question. So the question says, sorry, they want us to find space-time. So space-time is tau, okay? Both reactors, you have to find space-time for the first PFR and space-time for the second PFR. Okay, so space-time is exclusive to the one reactor. So if you have two reactors, you have space-time for the first reactor, you have space-time for the second reactor. So if you wonder why, you realize, right, the formula is space-time over volume per initial volumetric flow rate. You remember, right? When you have two reactors in series, both will have different volume. They can be the same, they can be different. So when you have different volume, definitely the space-time will change also. So you have to find both space-time of the first reactor space-time. So you can say tau PFR1, you have to find tau PFR2. So it's something different, right? Because all this one you learn, find the volume PFR1, V PFR2. This question, they want you to find tau of PFR1, tau of PFR2. Okay, so to achieve 40% intermediate conversion, X1 is 0.4, overall conversion 0.8. So your X1 0.4, X2 0.8. Okay, so these are the information that is given to you. So again, you remember what you have to first list out what information that you knew from the first question. So from the first question, the information that you know is, first of all, you find your CA naught. Okay, then you find your FE naught. So I have also my FE naught. However, you may ask, can we use the FE naught from question A? Okay, so this is the challenge. You must again understand what information that can be used in all the question, what information is only specific to that question. Because in this example, you have question A, B, and C. Not necessarily all information you get in question A, you can use in B and C. So you have to understand. So let me teach you. Okay. The information that you can use for all of the question, meaning part A, part B, part C, are the information given to you at the top part of the question. Okay, so remember kalau question tu ada A, B and C, only information yang part atas sebelum pergi part A, part B, part C yang kamu boleh guna untuk semua soalan. Okay, only the information given at the top part can be used for part A, part B, part C. But if the information is specific only to the part A, you cannot use it for the part B. So for example, in this question, from the information at the very top, the only thing that you can find was CA naught. So meaning that the CA naught that you find, you can use in part A, part B, part C. Okay, so because when to solve that CA naught, you only use the information at the top part. Okay, so next, what about FA naught? Okay, then you have to remember the FA naught you find in part A, and you only get FA naught because in part A they gave you epsilon naught. So in part A, sebab dia bagi kamu epsilon naught, sebab tu kamu boleh cari FA naught because you tahu CA naught, you know epsilon naught, you can find FA naught. But the epsilon naught is only specific for part A. Part B, you cannot use this epsilon naught because they do not mention, first, they do not mention you can use the epsilon naught. They do not also mention the epsilon naught. So meaning to say that the FA naught that you get in part A cannot be used in part B. Okay, again, I repeat, the FA naught that you get in part A cannot be used in part B sebab in order for you to get FA naught, you have to multiply with epsilon naught which is given in part A. So maksudnya hanya part A, soalan yang dalam senario A sahaja epsilon naught tu diberi. Ataupun senario A tu kamu tahu nilai epsilon naught. In question B, dia tak cakap kamu boleh guna epsilon naught part A, dia pun tak beri. So meaning that you cannot actually determine FA naught at this stage, and the only information that you have is actually the CA naught, the one that you get from the top information. Okay, so I hope you really understand sebab this is also something that students sometimes will make the mistake, that student assume information part A boleh guna dalam part B. Tak semestinya, kecuali dia clearly inform all the information is at the top of the question. Okay, so the only information that you can use is actually just the CA naught. Right, so again, come back. How do we solve this question? Okay, so again, I will go slowly sebab this is part yang kamu tak biasa. Sebenarnya kamu hanya solve cari volume, okay, cari FA naught. Dalam soalan ni dia suruh kamu cari space time. Okay, so come back again to the design equation first. Okay, regardless of how you got stuck pun, you use first, you know that in order for you to solve reactor in series, dia kena guna formula yang sama. Kamu tak boleh lari pada formula tu sebab reactor in series is still using that formula, the same formula. So contohnya, in the case of PFR, if I want to find the first PFR, the formula says the volume of PFR1 equals to FA naught integrating from 0 to 0.4 because my first PFR is converting from 0 conversion to 0.4 conversion, X1 kan? So the first reactor, right? So dx per minus RE. So this is the only formula that you have. Okay, so again, you have to then think back. Formula tu ada volume. Formula tu ada FA naught. dx per minus RA. So, formula ni tak ada apa yang kamu nak cari. It doesn't have space-time. It also doesn't have FA naught. So, you know that this equation is somewhat you may need to tweak or you may need to elucidate balik. Sebab kamu tahu equation ni sepatutnya digunakan. Sebab that is the only equation that you have. But the equation that you have right now cannot solve what you want and don't even have the information that you need. Okay, so then you have to think back. How does this equation correlates to what you want to find? So kalau kamu ingat, apa yang kamu nak cari, okay, I come back here. The one that you want to find is space-time. So you know space-time equals to volume per epsilon naught. So let me write it back here. Okay, so you know that to find space-time, saya copy ni terus. I copy here. Okay, let me do this like this. Okay, I hope you can see this clearly. You know that space-time for the first PFR must equal to volume of the first PFR over epsilon naught. So now kamu kena correlate kedua equation ini. So this is mathematics. This is somewhat you have to learn. Okay, macam mana kita nak correlate information sebab we know that the original equation tak ada benda yang kita nak cari. Benda yang kita harus tahu pun kita tak ada, which is FA naught. Okay, but we know that kita nak cari space-time. So we learn that space-time untuk PFR pertama must equal to volume of the first PFR divide by inlet volumetric flow rate. So, cuba kamu correlate balik the first and the second equation. So you can see here that the second equation ada volume PFR1. Okay, so I try to make it this color so that you can see. So I have volume PFR1. In my space-time formula pun ada volume PFR1. Nampak macam dah on the right step kan, dah ada correlation kan. Tapi formula space-time ada pula epsilon naught. Formula kedua saya ni tak ada epsilon naught. Tetapi you remember FA naught kan sama dengan CA naught multiply with epsilon naught. Kamu remember right? FA naught correlation dia. FA naught kan sama dengan CA naught multiply with epsilon naught. This is the correlation that you learn in chapter 1. Okay, again kalau kamu tak ingat, kamu pernah belajar chapter 1. Kita correlate concentration, molar flow rate dengan volumetric flow rate. So the correlation was concentration of A, CA naught equals to FA naught per epsilon naught. Therefore, FA naught equals to CA naught multiplied with epsilon naught. So instead of tulis FA naught, saya jadikan dalam bentuk CA naught multiplied epsilon naught. Bahagian bakar integral saya masih sama, saya tak kacau. Okay, so let's look back at this. If you understand this, cuba saya buat macam ni. Bila saya terbitkan semula, saya dah jadi macam ni, right? You realize that on my left hand side, I have volume PFR1. Right hand side, I have CA naught multiply epsilon naught multiply with the integral 0.4 dx per minus RA. So you realize that tengok balik space-time punya formula. Space-time formula untuk PFR1 sama dengan volume PFR1 divide by epsilon naught. So you can see that kalau saya tulis balik space-time for PFR1 sama dengan volume PFR1 bahagi dengan epsilon naught, bahagi dengan inlet volumetric flow rate epsilon naught. You can see here I'm now moving my epsilon naught from right hand side to left hand side. So sekarang kalau epsilon naught ni saya pindah daripada kanan ke kiri. Kalau di kanan dia adalah pengatas, bila pindah ke kiri dia jadi pembawah. So you see now I get volume PFR1 divide by epsilon naught, which is same with my space-time that I want to find. So what happens to my right hand side? Sebab epsilon naught saya dah bawa ke sebelah kiri. So belah kanan saya sekarang tinggal CA naught. Dan saya sambung balik dengan the integral part of dx 0 to 0.4 dx per minus RE. So again, I hope you understand. Sometimes saya rasa ni kalau saya tunjuk fizikal senang je kamu faham. Tapi online I find it a bit hard to explain. So I try again kalau Fadil tak faham. So ni adalah melibatkan manipulation of formula. Sebenarnya formula yang saya ajar ni semua formula yang kamu dah pernah tahu. Tapi at that time when we learn directly without knowing that this equation can be correlated to one another. So itu challenge dia sebab bila kamu belajar teori, dia adalah 3 separate equation kan. Tapi bila calculation, dia akan form satu soalan punya solution. So that is a challenge. Sebenarnya kita nak correlate dia. Okay, so again, I will go back again if you don't understand. So the original equation was volume PFR 1 equals to FE naught integrating from 0 to 0.4 dx per minus RE. Okay, so masalah equation ni adalah kita nak cari tau PFR 1. Okay, kita tak ada dalam equation ni. Lepas tu, kita tahu that dalam equation ni ada FE naught. Soalan kita tak beri information FE naught. The only information kita tahu adalah CE naught. Okay, again, sebab saya dah terangkan FE naught dalam part A tak boleh guna dalam part B. Sebab FE naught dalam part A, kita dapat daripada epsilon naught yang diberi dalam part A. So, you need to say that epsilon naught yang kamu dapat dalam part A ni, you cannot use in part B because the epsilon naught is only specific untuk soalan part A ataupun untuk design reactor dalam part A. Dalam part B, epsilon naught tu dah tak valid. Sebab tu kita tak boleh ganti epsilon naught itu. Hanya CA naught kita boleh guna. Okay, so that is the challenge now. Tapi that's how you kena correlate balik. So you know that space-time formula dia, you don't have to memorize, it's also given. So space-time PFR 1 sama dengan volume PFR 1 sama divided by epsilon naught. So kamu tahu that saya dah ada correlation, saya dah tahu perkaitan dia. Saya boleh check space-time. Kalau saya tahu volume and saya tahu epsilon naught. Okay, so equation yang original tadi, I already have volume PFR 1. So now I don't have epsilon naught. But I know my original question ada FE naught. So kena correlate balik. Saya tahu FE naught saya ni berkaitan dengan epsilon naught. Sebab FE naught sama dengan CA naught multiply with epsilon naught. So now instead of writing as FE naught, I write it as CA naught multiply with epsilon naught. Integration part belakang tu masih ada. Kita tak kacau part belakang. Okay. So bila kita ada correlation ni, kamu nampak dah, okay, belah kanan saya volume PFR 1. Belah kiri saya ada CA naught multiply with V naught multiply with the integration part. So kalau V naught di sebelah kanan, I bring to the left hand side. So when I bring to the left hand side, it automatically become pembawa, right? Because when it's at the top on the right hand side, you bring it cross over to the left hand side, it will become at the bottom. So that's why you get volume PFR 1 divided by epsilon naught. So when you divide, you have already find the space time for the first PFR. Belah kanan tu dah settle, dah tahu dah space time dia. Apa yang tinggal kat belah kiri? So belah kiri only left with your CA naught and the integral part. So you can see now I have already tweaked my space-time formula untuk mencari sudah menggunakan original formula yang menggunakan volume tu. Okay, so then now the integral part samalah, you change into the Simpson one-third rule. Okay, so yang part integral tu kamu integrate dalam bentuk Simpson one-third rule. Yang bahagian depan tu sekarang menjadi CA naught. Dan this one adalah sama dengan kamu punya tau space 1 ataupun space time for PFR 1. Okay, so you solve it as usual. So the space time for PFR 1 equals to CA naught 0.29, the CA naught. So the back part is dia daripada 0 to 0.4 kan, X1 is 0.4. And the first reactor is integrating from 0 to 0.4. Right, so in the formula, you will find that the first point is 1 per minus RA when my X is 0. The last point is 1 per minus RA when my X 0.4. Therefore, the middle one will be 4 per minus RA at my middle X. Initial X 0, Final x 0.4, middle x 0.2. So become 4 per minus RA 0.2. So when you know the 3 points, you just look back at your Simpson 1/3, you look back at the Levenspier plot. So you naik, tengok balik Levenspier plot. You know that for Levenspier plot, when my x is 0, 1 per minus RA 2.2. This is from Levenspier plot, So Levenspier plot. So next one. When my minus RA is 0.2, when my x is 0.2, 1 per minus RA is 3.33. Jangan lupa kamu kena darab dengan 4 because the Simpson 1/3 rule has 4. Okay, then the back part, when my x is 0.4, when my x is 0.4, 1 per minus RA is 5.13. Okay, so when you solve this, all right, then next we find delta x. To find delta x, saya rasa saya dah repeat banyak kali kan. Kita already taught you, I think you should have already understand. So delta x will be the gap between 0 to 0.2, which is 0.2, or 0.2 to 0.4, masih 0.2. So you can get the delta, you get your delta x as 0.2. So you solve this, the space-time, you get your space-time as 0.4 second. Kamu akan tengok nanti, nilai space-time kamu adalah dalam bentuk time. So kalau kamu tak sure, cuba kamu buat pembatalan unit. Kamu akan tengok that memang nilai final kamu, space-time kamu adalah dalam unit time. Which is correct lah. Meaning because I want to find space-time. Unit dia mesti dalam bentuk time. Okay, now we go to the second PFR. So again, I repeat, you have two different space-time sebab volume PFR tu 1 dan 2 berbeza. The volume changes, the space-time also changes. So what happened to the second volume, second reactor? Okay, so again, sama formula. Volume PFR2 sekarang sama dengan FA0 integrating from 0 to 0.4 to 0.8, x1 0.4, x2 0.8, dx per minus RA. So again, kamu ingat, kita akan buat step yang sama. Instead of using FA0, I change to CA0 multiply with epsilon naught. Kenapa? Sebab kita tahu correlation dia FA0 sama dengan CA0 darab dengan epsilon naught darab dengan integral 0.4, 0.8 dx per minus RA. So again, the epsilon naught on your right hand side, I move to the left hand side. So when I move at the right, it was at the top. When I move to the left hand side, it becomes bottom, right? So you get volume PFR2 divided by epsilon naught. This is equal to your space-time for your second reactor. So kamu boleh tengok sini sebenarnya adalah step dia adalah kamu melakukan sedikit perubahan, then you get what you want, which is what? Space-time for the second reactor. Tetapi sekarang, what happened to the left-hand side? So the left-hand side sekarang jadi tinggal CA0 sahajalah sebab epsilon naught saya dah pindah ke belah kiri. So it become CA0 integrating 0.4 to 0.8 dx per minus RA. Okay, so again, the integral part, kamu jadikan adalah bentuk Simpson 1/3 rule. So the integral part, you change it into Simpson 1/3 rule. Okay, so again, so now this is how you find the space-time for the second reactor. So again, to know the point. Okay, so first of all, CA0 is 0.29. So again, CA0 is 0.29. Delta X we discuss later. The 3 points. So you must imagine now the second reactor is integrating from 0.4 to 0.8. So the first point will be 1 per minus RA when my X is 0.4. The last point will be 1 per minus RA when my X is 0.8. So you know that your initial X was 0.4, your final X is 0.8, therefore the middle X will be 0.6. So this is the part that you have to be very careful sebab your initial X sekarang dah bukan 0. Dalam reaktor kedua, initial X kamu adalah X1. So X1 kamu 0.4, X2 kamu 0.8, the middle X is 0.6. Okay, so it becomes 1 per minus RA when my X 0.4, 4 per minus RA when my X 0.6, 1 per minus RA when my X is 0.8. So again, you go to the Levenspier plot, you check the values. So this is the part that you just go dalam plot, tengok bila conversion ni adalah nilai ini, berapakah nilai 1 per minus RA dia. So you can substitute directly into the equation. So part belakang tu okay. Delta X, so again delta X is the gap, right, between initial X 0.4 to middle X 0.6. So 0.4 to 0.6, the difference is 0.2. Kalau kamu tengok kat belakang juga, 0.6 to 0.8, the difference is still 0.2. So that's why the delta X is 0.2. So now you get your space-time for the second reactor. When you calculate, you get 1.17 seconds. So you see, when I have two PFR in series, the space-time also will be two separate space-time. Sebab you dah belajar kan, even volume pun akan berbeza. Therefore, space-time pun akan berbeza. Okay, so this one I will give you a bit of time. I have another one part C sahaja to settle. So I'll give you maybe 2 minutes and for you to understand. Okay, I hope you understand. Okay, then I will go to the next question. All right. Okay, all right. So we go to the last part, question C. Okay, so just to inform you, I left one question, question number 5, which I will not discuss in class. So I hope that when you have extra time, if you would like to just determine whether you understand or not the lesson so far, you can attempt question 5 by yourself. The questions are already on VLE and the questions is also attached with the question comes with the final answer. Jalan kerja tak ada lah, final answer ada. So you can at least determine whether you are right or not when you attempt the question. Okay, so the last question for today is that calculate the space-time for two CSTR in series. So now they want you to find space-time pula. Kalau you have two CSTR in series, means tau CSTR1, tau CSTR2. So tadi kita find tau PFR1, tau PFR2. Now you have to find tau CSTR1, tau CSTR2, given intermediate conversion as 10%. So your X1 is 0.1. With the overall conversion of 60% in the second reactor. So dia kata X1 0.1, X2 0.6 sebab kamu ada dua reactor, right? So X1 0.1, X2 0.6. So again, okay, the only information yang lain yang kamu boleh guna selain daripada X1, X2 adalah information or the calculation that you have done based on the top information. So the only other information that you can use based on the top information was the CA0. Okay, so only this information yang kamu boleh guna. Dan lain semua kamu tak boleh guna. Okay, so again, kalau kamu perasan, dia almost menggunakan konsep yang sama. Saya kena tahu formula yang saya ada dan apa yang saya nak cari. Okay, so you remember what the original formula untuk cari volume CSTR1 adalah volume CSTR1 equals to FA0 X1 per minus RA X1. So this was the original formula. So again, the challenge is I don't have space-time, which I want to find. Tau CSTR1, I don't have. And I also don't have FA0. Okay, but you realize that in the question, space-time for CSTR1, formula dia akan menjadi volume CSTR1 over epsilon naught. So kamu dah kena correlate apa yang kamu ada dan apa yang kamu nak cari. Kamu tahu dah nak cari space-time untuk CSTR1 dan menjadi volume CSTR1 divide by epsilon naught. Okay, so kamu tahu dah bahagian yang FA0 ni kita dah tak boleh guna dalam bentuk FA0. Tapi kita tahu dah FA0 is equal to CA0 multiply with epsilon naught. Okay, again yang ni bukan benda yang baru. Kamu dah pernah belajar berkaitan antara FA0, CA0 dengan epsilon naught. So FA0 akan sama dengan CA0 multiply with epsilon naught. So X1 per minus RA1 masih sama. Okay, so again, what is the function of knowing this? So let's say I write it like this. So bila kata macam ni, saya rasa kamu boleh nampak dengan lebih jelas. Kalau kamu nampak daripada equation ni, maksudnya belah kiri saya ada volume CSTR1. Okay, on my right hand side, I have CA0 epsilon naught X1 per minus RA at my X1. So if I move this epsilon naught from right to left, so from the top, it becomes bottom at the left. So you get on your left hand side, volume CSTR1 divided dengan epsilon naught. This is actually your space-time for your first reactor. So by removing the equation, kamu dah dapat dah belah kiri kamu lah apa yang kamu nak, which is the space-time for the first CSTR. So what happened to the right hand side? So right hand side you are left with CA0 saja. Sebab epsilon naught kan kamu dah move ke belah kiri. So belah kanan tinggal CA0 X1 per minus RA1. So now you have already get left hand side apa yang kamu nak cari. Right hand side tu kamu solve lah. Kamu dah dapat apa yang kamu nak. Okay, so from the information, CA0 you calculated initially, yang paling atas kamu calculate, kamu tahu CA0 kamu 0.29. So done. Okay, X1 is 0.1. Your conversion in your first reactor is only 0.1. So then you go and check your Levenspear plot. When my X is 0.1, 1 per minus RA is 2.7. Okay, so ni daripada Levenspear plot yang awal-awal kan, Levenspear tu kan diberi pada bahagian atas, right? So you go back and check the Levenspear plot at 0.1x, my 1 per minus RA is 2.7. So you terus multiply with 2.7. So when you multiply, you get your space-time for first CSTR as 0.07 second. Okay, so again, you can always do unit cancellation. Kamu kan nampak that unit final space-time kamu tu mesti unit this is the unit time. Okay, sebab if you do it correctly, the equation, unit dia tak akan lari daripada unit yang kamu nak. Okay, so done for the first CSTR. Okay, let us go to the second CSTR. So, konsep dia hampir sama. Tapi kami ingatkan formula dia kan dah berubah sedikit. So, for the volume of CSTR2, if you remember, is equal to FA0. times with x2 minus x1 per minus RE at my x2. So, sama konsep. Instead of tulis FA0, saya tukar jadi CA0 multiply dengan epsilon naught. Yang bahagian lain kamu tak kacau sebab saya hanya ubah FA0 itu menjadi dalam bentuk CA0 darab dengan epsilon naught. So bahagian belakang x2 minus x1, bahagian bawah minus RA and x2 pun tak berubah. So again, kenapa saya buat macam ni? Sebab saya tahu that okay, let me write back so that you can understand. So that when I write back, so I can see that if I move my epsilon naught from right to left, dia akan menjadi pembawah dan bahagian kiri saya kan dah ada volume CSTR2. So volume CSTR2 divided by epsilon naught, you already get your space time for your second CSTR. So when you move the equation, you realize that bahagian kiri kamu dah apa yang kamu nak, which is the space time for the second reactor. So belah kiri kamu akan menjadi tinggal dengan CA0 in bracket x2 minus x1 divided by minus RE at x2. So you just solve as usual. So CA0 was 0.29. X2 is 0.6 from the question, X1 is 0.1, and from the level sphere plot, when your X is 0.6 and your X2, your 1 per minus RA is 8.85. So kamu terus darab saja sebab dia terus bagi kamu 1 per minus RA. So when you solve, your space time for your second CSTR is 1.28 second. Okay, so you already solved. In the part C question is to find the space time, the same macam part B, tapi part B kamu cari space time untuk PFR. Question C, part C is to find space time for CSTR di mana both are in series. So basically when you have reactors in series, you have to find the separate space time for the reactors. Okay, so this is all for today's tutorial. I will not go to question number 5. Now question number 5 is a practice question for you. So when you have extra time, you want to find out if you can or cannot understand, you can attempt question number 5 by yourself. Dalam WLE dah ada jawapan akhir. So kamu boleh compare, tengok kamu betul atau tidak. Okay, so we already completed chapter 2 tutorial. So on Thursday or Friday, depending kamu T1 atau T2, we will meet again for 2 hours for your lecture chapter 3. So please don't miss because test akan sampai lecture chapter 3, right? So that's all for today. I will see you next Thursday. I will see you this Thursday or Friday according to your tutorial time. All right. So thank you everyone. Have a good day and for your next class. All right. Bye.